Okay, this is the answer key for your test. It was gleaned from Brown, your textbook on the 10th edition. There are questions number 30, 44C, and number 52 from chapter 17. The first question, and I paraphrase, is what combination would you use to make a buffer, or what combination of acid and its conjugate base would you use to make a buffer of pH 4.8? The selection of acids that you have is formic acid, propionic acid, and phosphoric acid. And I've listed the Ks for each one of the respective acids. Recall that taking the negative log of the Ka gives you the pKa. And if you remember what the Henderson-Hasselbalch equation implies, that the pH is equal to pKa plus the log of the concentration of A minus over HA. So A minus represents the conjugate base, HA represents the acid. So if you have equal concentrations of these two substances, if you have equal concentrations of the acid and its conjugate base, this is going to give you 1. So let's say the value here was 0.1 molar, and the value here was 0.1 molar. 0.1 over 0.1 gives you 1, and the log of 1 is 0. So when an acid is half ionized, or half neutralized, whatever you want to say, the pH is going to equal to the pKa. So what we're looking for here is a buffer system that is going to have a pH, that's going to have a pKa close to 4.8. And as it turns out, propionic acid with propionate has a pKa of 4.89. So we're very close to the target pH. So that's the acid we're going to use. The buffer needs to be prepared with a pH of 4.8. The pKa of propionic acid is 4.89, which is very close. Only 0.09 pH needs to be reduced. And we're going to do that by adding a little extra of the propionic acid that's going to lower the pH. So moving on to the next board, we use the Henderson-Hasselbalch equation. We plug in the numbers that we do know. The pH is equal to 4.8, the pKa is 4.89. Solving for the log of A minus over HA. So we got negative 0.09 is equal to the log of conjugate base over the acid concentration. We take the inverse log of negative 0.09, and it gives us 0.8128. Then we say, let X equal the milliliters of propionic acid used. We know that we have a 0.1 molar solution of propionic acid and a 0.1 molar solution of its conjugate base propionate. So if X is equal to the milliliters of propionic acid, and we know that propionic acid is in greater amount than its conjugate base, then the 0.8 will be attributable to the propionate. So X plus 0.8X is going to give you 1,000 milliliters. The total volume of your buffer has to be 1,000 milliliters. 1.8X is equal to 1,000 milliliters. We solve for X, we find out that the 551 milliliters of the mixture is the propionic acid, which means the rest of it has to be the propionate. And that turns out to be 448. After sig figs, the final answer is a buffer solution with 552 milliliters of propionic acid and 448 milliliters of propionate would have a pH of 4.8. In the next question, we are asked, calculate the pH at the equivalence point in titrating 0.1 molar solutions of each of the following with 0.08 molar sodium hydroxide. And the part C is sodium hydrogen chromate. So I show that this solution of sodium hydrogen chromate into the hydrogen chromate anion and a proton. Sorry, the sodium hydrogen chromate dissociates into sodium cations and hydrogen chromate. The hydrogen chromate dissociates further into hydrogen ions and the chromate anion. If we assume a 1 liter solution of this substance, we're going to say the number of moles is equal to molarity times the volume. So we find out that we have a 0.1 moles of hydrogen chromate and of chromate. And if we're going to be titrating with 0.08 molar sodium hydroxide solution, we're going to need a certain amount of that solution, which is going to be more than 1 liter because we started off with 1 liter, and this is a lower concentration. So our number should have to be bigger than 1 liter to titrate a concentration of 0.1 molar. And it turns out it's 1.25 liters. So now the total volume of our solution with the titrant and the substance being titrated is going to be 2.25 liters, which means our chromate solution has been diluted from a 1 liter solution, which was over here, to one that has a volume of 2.25 liters. So how do we find the concentration of the chromate after dilution? We know we had 0.1 moles of the stuff in the solution, and that now the solution volume is 2.25 liters. So now the concentration is going to be 0.1 divided by 2.25 liters, the new volume, and it's going to be 0.04 recurring molarity. Then we took the Kv value, we find actually the Ka value for hydrogen chromate. We put it into the dissociation of water, Kw, to find the Kv value for this substance, which is left over after titration. And we plug it into the, we could do an ice table if you like. The end result is you get x squared over 0.04 minus x. But because the value of x is going to be a tiny number, this is 10 to the minus 8, so if you took the square root of this, you can still get 10 to the minus 4, which is 100 times bigger than the number 0.04. So we know that the value of this number x is going to be a very small number. So I made the approximation that the minus x part is not going to put a dent in the 0.04. And I did the calculation. I got that x squared is equal to 1.3 recurring times 10 to the minus 9. X is equal to 3.65 times 10 to the minus 5. So it turns out my approximation was correct. 10 to the minus 5 is way smaller than 0.04. This also corresponds to the hydroxide concentration. So I do POH is equal to negative log of OH minus. That gives me the POH. We also know that pH is equal to 14 minus POH, and the pH is 9.56, which is what we were asked to find. So we see that when a weak acid is titrated with a strong base, the result is a slightly basic solution, because the conjugate base of the weak acid induces some basicity in the solution after it ionizes. This chromate anion will abstract protons from water, reconstituting the hydrogen chromate, so that it'll make the pH go slightly above 7. It'll have a slightly basic solution after neutralization. The third question asks us to calculate the solubility of a marginally soluble salt. So lanthanum fluoride is not a soluble substance, but a tiny amount of it does dissolve when you put it in water. So we're asked to find what its solubility is in pure water, in a solution of 0.01 molar potassium fluoride, and in a solution of 0.05 molar lanthanum chloride. So this is a regular KSP calculation, and these two are KSP calculations in the presence of a common ion. In the first step, we find first of all the molar mass of lanthanum fluoride, which is 195 grams per mole. We look up the KSP of lanthanum fluoride, which is 2 times 10 to the minus 19. We see that lanthanum fluoride dissociates into the lanthanum cation and the fluoride anion. And we also notice that 3 fluoride anions are released for every lanthanum cation. So the concentration of fluoride is going to be 3 times the concentration of lanthanum when it does dissociate. So when we represent it with the letter X, if we let X equal the lanthanum concentration, then the fluoride concentration has to be 3 times that. And we're going to replace these letters, these atomic symbols, with the value X. So X and 3X, this symbolizes lanthanum, this symbolizes fluoride. Notice that it's raised to the power of 3. And when we do the algebra, we find that the KSP value is equal to 27x cubed. We solve for x, or not x cubed, x to the 4th, sorry. X to the 4th is equal to 2 times 10 to the minus 19 divided by 27. That gives us x is equal to 7.4 times 10 to the negative 21. So then we take the 4th root of this number to find the value of x. Turns out to be 9.2 times 10 to the minus 6 molar. So that's the concentration of lanthanum fluoride that dissolves in pure water. But the question asks us how many grams in a 1 liter solution. So we multiply by the molar mass of the lanthanum fluoride, and it turns out we get 1.8 times 10 to the minus 3 grams per liter of solution. We're only allowed one significant figure, so we record it as 2 times 10 to the minus 3 because 1.8 will round up to 2. 2 times 10 to the minus 3 grams of lanthanum fluoride will dissolve in a 1 liter solution. In the second question, we're asked what's going to happen if we add potassium fluoride to the solution. So now we have a common ion inhibiting the dissociation of lanthanum fluoride. We set it up as a KSP equation. Notice I did a nice table for this one to keep everything straight. The lanthanum, before it starts to dissociate, the lanthanum concentration is 0. A certain amount X dissolves, and at equilibrium we have an amount x in terms of concentration. Before dissociation starts, at the outset, because of the potassium fluoride, we have a 0.01 molar solution of fluoride anions. Whatever amount of lanthanum fluoride dissolves, if we call lanthanum X, you're going to get 3 times as much fluoride dissolving. So the amount of fluoride that dissolves, we're going to call 3x. So at equilibrium, it's going to be 0.01 plus 3x. So the KSP value is equal to x times this. And we could solve this, but we'd have to use a graphing calculator to do it if our math is not up to it. But I think we can safely say that this number, 3x, is way smaller than 0.01, because we're looking at something on the order of 10 to the negative 19. So I ignored the 3x part, and I just wrote x times 0.01 cubed. And that simplifies to 1.0 times 10 to the minus 6x. When we solve for x, we find that x is equal to 2.0 times 10 to the minus 13, which confirms my hypothesis that x would be way smaller than 0.01. This number is 12 orders of magnitude smaller. That's a trillion times smaller. So our calculation is not rendered inaccurate by ignoring the 3x part. So in a 1 liter solution, this times the molar mass of the lanthanum fluoride will give you that 3.9 times 10 to the minus 11 grams of lanthanum fluoride dissolved. So you see a lot less lanthanum dissolves than in the first case because of the presence of an interfering common ion. And then we're only allowed one significant figure in the final answer, so the answer ends up being 4 times 10 to the minus 11 grams of lanthanum fluoride dissolved in the presence of potassium fluoride. In the third part of the question, we now have a different interfering ion. It's now the lanthanum that is in the way. Its concentration at the outset is 0.05. X amount of lanthanum dissolves further as a result of the presence of the lanthanum fluoride. So at equilibrium, we have 0.05 plus X. Again, the fluoride concentration is going to be 3 times higher. And at equilibrium, we have 0.05 plus X times 3X all cubed. We're going to solve, again, we're going to ignore the presence of X because X is way less than 0.05 in my opinion. And we'll see later on whether I was right. 1.35x cubed is equal to the KSP value. Solving for x cubed, we get 1.481 recurring times 10 to the minus 19. So again, this number is way smaller than 0.05, so we can ignore that part there. When we multiply this number by, when we find x cubed, I'm sorry, I'm jumping ahead a little bit. When we take the cube root of this number, we get this number, and this number is in fact also very much smaller than 0.05. So the approximation was valid. Then I take the molarity of this amount of lanthanum fluoride that dissolves times the molar mass of lanthanum, and we get how many grams of lanthanum fluoride dissolves in 1 liter of solution. One significant figure is all that we're allowed, so 1 times 10 to the minus 4 grams of lanthanum fluoride dissolves. And that would be the end of the question.